In the previous video, we have seen how we can add audio file and how to, with the help of Colab, and where the audio file was saved in the Google Drive itself, and Google Drive was connected with our Gmail. In this particular video, we will be seeing how to extract the features from the audio file shared. For example, the audio file which I shared here is car001.web file, and which is stored in my drive, uh, which is attached to my Google Drive itself, with my Gmail. And we have shown in the previous lecture that one Colab notebook will be created. In the Colab notebook, there is a data set, and among that given data set here, that car001 is one of the audio file which is already there. So whenever we want to extract the features of audio file, that audio file should be attached in our Gmail, or at least in the system. So car001.wav is one audio file which is already attached here. Now I want to extract the features of that audio file. So very first, this all we have seen in the previous video itself. The time domain graph of the audio file is being plotted, and we have played also, and we could hear that audio file is enabled, and we can hear the sound. It is making sure like what the audio file I have attached, it is working fine. Now we'll be looking for some of the features, and very first feature here is spectrogram. These features are with respect to time domain analysis of signal, and very first feature is spectrogram. And for that, this is a code that it is telling the input, which is the data which is stored in the variable x is librosa.stft, and stft is a full form of short time Fourier transform of the given signal x, which already I have mentioned in the previous cells. Once the STFT is being calculated, we will be taking the log of that value. So STFT in DV is calculated using this particular, what we can say, syntax. Librosa, which is the basic library, amplitude underscore 2 underscore DV, and the absolute value of x, which is coming from the previous third cell. Then PLT, the figure, and figure 20,5 is indicating like I have x-axis size 20 and the window size in y is 5. Librosa.display.spec show dependence on what the decibel value we are having, and the sampling frequency, the x-axis, what all the time duration we have taken, and the y-axis, that is the frequency. PLT.title, PLT is the library, matplot library is imported as PLT. PLT.title, which is telling about the spectrum of audio file, which is as a title, which displayed here. And PLT.colorbar, which is saying color visualization of our spectrogram feature of our audio file. So all of us, we can see here, this particular waveform which is being plotted is with respect to time in the x-axis, and frequency on the y-axis, and there is a variation in the color. We can see majority of the color after 6,000 hertz frequency or nearby 5,200 hertz frequency is blue, and below that between 0 to 5,000 hertz, there is a mix of frequency. And what this particular color is indicating, that we can see on this particular color bar, where 0 is mentioned here, and the negative frequency is marked on the below y-axis, and positive frequency is marked on the above that x-axis, above that vertical side of y-axis. We can see that negative frequency is marked more or less shade of blue, and we can see so much in that particular audio file, so many frequency that is above 6,000 hertz was very less, or more of the that sound intensity that is above 5,000 kilohertz is marked on the upper side, and this is a mix of that, where there is a visibility like we are having energy which is available within the range of 0 to 20, and a mix of some frequency, because some part in the audio we can see there is a pitch more, energy more, and some part of the audio there is a less energy. So that is the reason there is a variation in the energy, which is which can be visualized in this particular graph. So second feature of this time domain analysis of audio signal is, we will be looking for MFCC. So MFCC, as all of us we know, it is one of the important feature whenever we are writing any of the audio parameter extraction. MFCC play a lot role. It is a complete detail of this we can see in many of the content given in the books or in the net. So here we will be seeing how MFCC is going to give the features here in terms of code. So again, import Librosa we have done before, audio path which is added for this car001 file, and the value which is stored in variable y and sampling frequency SR with the audio path given before in the upper cell, and MFCC equal to librosa.feature.mfcc. This is a syntax, and y is given as the data is stored in y with the sampling rate, and NMFCC, that is 40 value. This value can be changed and little bit we can visualize. Then we are printing MFCC.shape and what all the MFCC and this sampling frequency, and I want X also to be plotted, that is Librosa.display. So what all we are displaying is MFCC coefficients with this particular sampling frequency, and then X-axis is given as time. So this is a X-axis time, and this is all MFCC coefficient. As we can see from one audio file to other audio file, there is a variation happening here. For example, I have two audio signal here. One is car001 and one more signal. We can make out how the difference is occurring because it is being calculated with this is one more spectrum and one more MFCC. If I have, I can show you. Otherwise, you can take one different audio signal and you can plot that and you can visualize there is a difference happening or not. So after MFCC, the third feature which we are seeing here is our chroma. So chroma is again indicating the spectrum, power spectrum, and there are 12 features, 12 particular band is defined, and it is basically used for music instruments. So we can see here S is equal to np.abs librosa.stfty, whichever the value we have calculated before. Based on that, chroma is being calculated and it is being appeared here. It is again a time domain feature, time and the pitch of class, and we can see there is a mix of the color band which is changing from one particular time instant to other particular time instant. So that's all.